Mm-hmm. 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 Okay, thank you for coming back. And this is the last hour. And let's see. So we were discussing random variables. Let me enable chat also. Any questions before any? Before we restart the course content? No? Okay. So let's get back to my screen share, and then I'll continue from we were doing screen share. Hopefully, you can see my course content file, and this is the. Let's see. I still have my stuff. Yeah. Okay. We have been discussing these things before the break. So we have three types of random variables, but in this this course, we will be focusing only on discrete and continuous random variables, right? The mixed ones are not necessary here. So, as I mentioned, you have a PDF and PMF and CDF, and you should know already these things. MGF, CAHF, and probably generate PGF. This will be the beginning of our discussion from next Friday, right? So I have gone through the discrete case. Here you have to work with the probability mass function. Then the second case is continuous random variables. Here you have to work with the PDF, right? However, if you want to work with the CDF, it could be any type of random variable, and it can handle that. Okay. So let me try to give you some connection between these two. So if I so the continuous case, let's see my pen working. This is the pen. Let's see. Okay, so here is the pen. So let's say I have in this particular case, I have a continuous random variable, right? So in this case, this is the relationship between the PDF and the CDF. So f of A, my CDF had some argument A. It's simply, what you do is the following. So you go from negative infinity to A, and you get the PDF, and you compute the area under the PDF. So that's the connection between CDF and PDF. Right? So it's pretty simple. If you know a basic density, I can calculate the CDF, right? So let me give you a also let me quickly mention a couple of properties of CDF and PDF. So these are the props. So the first thing is a PDF is a non-negative function. Okay, it cannot be negative, because if it is negative, it doesn't make sense. I don't want to work with negative probabilities. So this must be a non-negative function. Then number two is the total area under the PDF is equal to 1. Okay, so this tells me that total probability of this experiment is 1. Okay, so if this makes sense, because if you have an experiment, something will happen. So if something, there are a number of outcomes. One of them must happen by definition. So that fact is reflected in this equation. Right? So all of the outcomes, and sum over them should add up to 1. Okay, so that's the second. And so the likewise, I have number 3. I have some properties of CDF. So this one should be, first of all, CDF at negative infinity should be equal to 1. Sorry, my bad. Should be 0. Okay. And f at positive infinity, this should be 1. Okay. And number 4, if you take your CDF and differentiate df dA, now this is actually f of A, and this is non-negative. So what that means is f A is decreasing as A increases. Okay, so that's the basic as A is increased. So in other words, another way to say that is if some A is greater than B, so these are real numbers, right? Okay, not complex or anything. Real numbers. If A is greater than or equal to B, then f of A is greater than or equal to f of B. Okay, so these are the critical properties of the PDF and CDF. Let's see. Okay, so I have to mention a bit about the discrete case. Now, remember, in the discrete case, the random variable is defined on a set of countable points. They are countable, right? So they are discrete. So in this case, I cannot differentiate. That's not very meaningful. And also integration like calculus based integration is not meaningful. So what we have to do is the following. So if I want to, so this is the discrete case, right? So if you want, in this case, I cannot use a calculus, conventional calculus. It's not going to work because I'm working with discrete numbers, right? So how do I go from Px, my probability mass function, to CDF, f of A? Right? So that's the question. So also let me quickly mention a couple of properties. Number one, now the probability mass function is also non-negative. Okay, it cannot be negative. So Px is zero or positive quantity, right? Number two, if you sum all Px values or all possible x, the sum is 1 as before. So this again tells me that the total probability is equal to 1, which should be the case. Right? It means the whole random experiment, if you conduct, you're going to see one of the outcomes. That's what it means, right? Some of the all different outcomes is equal to 1, the probabilities of those, right? So these are two basic facts. Now, how do I get the CDF from PMF? So let's do that. So number 3 here, to do that, you have to recall the definition of CDF. Remember, this is the probability that my random variable less than or equal to A. Okay. So how do I compute this? So this means I have to add all outcomes that satisfy this condition. In other words, x is less than or equal to a. So all I have to do is the following, right? I go and pick my probability mass function, and I look for the x values that satisfy this condition, x less than or equal to a. So this is sigma x less than or equal to a, right? So this is how you compute from px to CDF, right? So you have to do this for all possible arguments here. Okay, so you have to move this a for pick any a value and compute this, right? So on the right hand, the sum is computed for x values less than or equal to a. So that's how you compute the CDF for the discrete case. Number 4, how do I get the PMF from the CDF? Now, to do that, we have to do the following. Let's say I want to calculate my P of x, right, probability mass function at some small x. So what we have to do is you have to go to the CDF, and then you have to look at the upper limit of CDF at x and subtract the lower limit. Let's say, let me call it fx minus. Okay, so you mean so the CDF will have a discontinuity at particular x. This is the this is my real axis, right? Okay, so the CDF will have a discontinuity because this is a discrete random variable, right? Not everywhere. This will happen only at a countable set of x values. For a countable set of x values, you have discrete jumps happening on the CDF, right? So you look at these jumps, and you have to compute the height of that jump. Okay, that height is equal to the value of the probability mass function at that point, and you have to do this for all members of the support. Remember, a discrete random variable has a discrete support, set of numbers where the random variable probability mass function is non-zero, right? So you have to do this computation for all such elements of the support, right? So these are some of the basic ideas of probability mass function, probability mass function, and CDF and PDF. So for the time being, let me stop the screen share and see if you guys have any questions before we are there any questions on the stuff we have been discussing? Okay, can you explain the point 4? Okay, I'll go back to the remind. Okay, yeah, I'll go. Unfortunately, I don't know if this is possible. When we do a screen sharing, I cannot see the chat. I have to learn. Hopefully, I'll learn this soon. Yeah. So there are 2 questions. Okay, can you explain the point 4? And does x plus denote the x greater than a? No. So that's another thing. So let me go back and check this. Check these things, right? Point 4. Point 4 and x plus. What does that mean, right? So maybe I can go to the. Let's try the the whiteboard. I haven't. Let's see, share screen. I haven't used this before. Let's see, this is the whiteboard. Let's see. You guys can see this, right? Okay. So what what is the meaning of x plus? Okay. So what does that mean is this is applied to a function, right? So some functions are not continuous. So this is true for the case of CDF of a discrete random variable. Okay, so this is my x. So sometimes at particular, let's say A, my function has a left limit and the right limit. So the upper and lower limit. So x plus, let's say A plus, f of A plus is the upper limit of f at x is equal to A. Okay, so that's my kind of a informal notation. Some other books may have a different notations. So does that answer your question? Or okay, hopefully that makes sense. So let's go back to point 4. Is that the question you had? Yeah. Okay. So basically, if you plot, I didn't have time here, but if you plot the CDF for a continuous random variable, CDF is a continuous function. Okay, continuous means that there are no breaking points in the graph. Okay, that's not true for discrete. Discrete CDF will have a countable number of jumps, and then we have to. Those are the probability mass points. Okay. Hopefully that makes sense. So let's go back to my PDF. Let's see. So in my PDF, I have given you in section 1 some basic probability models or random variables. There are many more, but for this particular course, it's enough to know these the properties of 1 to 5, Bernoulli, geometric, Pascal, binomial, and Poisson random variables. Okay, so And let me try to, again, we don't have a lot of time to go through each one in detail, right? But let me quickly mention few things. Okay, so each in my notes, for each random variable, I have given the probability mass function, mean and variance, and there are a few more details, right? So let's see. Let's go through one by one, and okay. So the Bernoulli is the simplest random variable. Okay, the support is just a 0 or 1. So that means my random variable it takes only two values, either 0 or 1, right? And the probability of 1 is P. Probability of 0 is 1 minus P. Now in lots of books and my notes, I will also use the notation Q, which is 1 minus P. This is the probability of failure. Now, this I should mention F, right? So when we are thinking about Bernoulli random variables, we think about a very simple experiment. Now it could be anything, okay? So I have a random experiment, okay. You could be asking somebody to do something and they say yes or no, okay. You could be applying for a job, you get a yes or no answer, right? Or anything, like any you are voting for yes or no. You're running or not, you're eating or not, whatever, any binary situation. So we, our random experiment, we have two outcomes. One is what we call a success, and that is what we observe, right? Success usually denoted by 1. And a failure is the whatever negative outcome, okay? That's denoted by 0. Okay. Now, no, S and F are not literal. Like that doesn't mean it has to be an actual success. Okay. For example, somebody, you can check someone is dead or not, okay, right? So if it's a dead, we can observe dead. That is our success. Now that's not real in a literal sense, but this is just a label. That's what I'm trying to say here. Okay, so I will use this notation always. Okay, in an experiment, success is 1, failure is F. It's denoted by 0. Okay, so the Q is the failure probability, and P is the probability of success in each experiment. So, and P is between 0 and 1, and Q is also between 0 and 1, and so on. So, I don't have to say much more about this random variable. It's a very simple. The probability mass function has only two values, P and Q. Okay, and we can easily prove that the mean and variance are P times Q. The variance is P times 1 minus V. This is another way of saying it is P times Q. So Bernoulli is very simple and it's not that interesting. So let's get into the more critical interesting one. Again, I don't have time to give you a detailed explanation here, okay? We can think of a geometric random variable as a sequence of Bernoulli experiments. In other words, what we are doing is we are running a Bernoulli experiment. In other words, every time you can only get a F or S. So if I have a happen like that F, this means I have to continue. Okay. See, because you have to toss the coin until first head comes off. So this is my S, the success condition, right? So the experiment is repeated until the success condition is met, right? So if I get F first time, I have to continue the experiment. So let's say I do it again and I have F again. Okay, you can imagine this happening. You apply for a job. This F first time, you apply for F second time. Maybe the third time you're lucky and you get the job. So S. Now these are not the random variables. Okay, the random variable is the number of times we had to do the Bernoulli trials. Okay, so in this case, X is the random variable and the value of X is 3 here because this is the total number of repetitions. Okay, so in this case, X can be 3. Now, in general, X can be 1, 2, or could be infinity up to. And so it's a very this PMF has a geometric decrease. So if you plot the PMF, X and P of X, which will be just a line diagram, 1, 2, 3, 4, and so on. The C at 1 is the highest value, like plug in X equals 1 here is P. The next one is smaller than that. The next one is smaller than that, and so on. Okay, so it's a geometrically decreasing. Hence the name geometric random variable. Okay. Now again, I cannot prove any of these things, which we don't have time. So there are interesting, very really interesting things about this random variable. I mentioned few of those. This is the average. This is the variance, right? So for example, let's say my experiment is this. Experiment is toss a fair coin until head H comes up. Okay. So X is the number of tosses needed. Okay. So if I do that, now my X can be 1. In the first toss I'm getting heads, or it could be 10. I get a 9 tails, and the next one is a heads come up. Okay. So in this case, I can see that my X is a geometric. It's a fair coin, so heads and tails are equally likely. So that means it's a geometric, and then my parameter is a success probability, which is the probability that heads come up, and that's equal to 0.5. So in this case, on average, I will take 2 tosses because my E of X is 1 over P, so that's equal to 2. Okay, so on average, I'm going to need 2 tosses to complete this experiment. Okay, so again the completion condition is a H comes up. Okay, that's the success condition. Okay. Now there are few other interesting properties. I don't have time. As I mentioned, we want to get into the most advanced stuff as quickly as possible, right? So the Pascal is the next random variable, this one. And this one is a generalization of geometric random variable. So this is a generalization. Our stopping condition is not just 1, but any arbitrary number that you want to specify. So let's say I toss the coin until k heads come up. What is k? My k is the parameter. If k equals 1, I'm back to geometric case. Okay, k equals 1 is the geometric random variable. We don't have to go back there. But let's say my k is 3. Okay, that means I have to continue tossing the coin until 3 heads come up, not sequentially, but any time. Okay, so it may look like this. Okay, it could be tail, tail. The second toss is tail. Okay, head comes up, then 3 tails, then I get a heads and head. Now I stop the experiment because the condition for the success condition, k heads come up, has been completed, right? So we met the success condition. So I can stop the experiment. 3 heads have come up. Now that's not the random variable. Random variable is the number of tosses needed in this particular case. So that turns out to be 3, 6, 8. So x is 8 here. Okay. So this is the definition of a Pascal random variable. And here is the domain or the support, and here is the probability mass function. So we can use this probability mass function to compute, for example, observing this probability. So if I want to compute the probability of this sequence, probability of exactly getting this thing, what I have to do is I have to go to my px, and I have to compute p of 8. Okay, so in this one there are a number of parameters. So this will be computed like this. So my x is 8 in this case. So 8 minus 1, choose my k is the number of heads needed for the success of the experiment. So k is 3 in this case. So it's a 3 minus 1. So you guys hopefully know the binomial notation. So and the p in this problem is p is half. So p is a half success to the 3, and the 1 minus p is also half. So that's half. Okay, and x minus k. So x is 8 minus 3. That's a 5. Okay, so that is the exact probability of getting this outcome. Oh no, that's not really true. Actually, I made a mistake. This is the probability. Let me say that. this is the probability that x is, I made a mistake, x is equal to 8. Okay, that's, which is not the same as the probability of this particular sequence. Okay, this is just a one realization of x being equal to 8. Anyway, let's not get into technical details here. Okay, hopefully you get some sense of the Pascal random variable. Now there are one more, there's two more, but let me try to explain the binomial one at least before we stop. So the binomial random variable is also related to the Bernoulli random variables. However, here is the difference. In this case, we repeat our experiment fixed number of times. Fixed number. Okay. That means it is not a variable like in the geometric or Pascal. You know, in that one, the number of repetitions will continue until you hit the success condition. Now that's not the case here. Here, the number of repetitions is fixed beforehand. We know it. Okay. So, for example, you can say that we are playing some games, hockey season, like here. Okay. Now this is here in Canada, we have a hockey league, professional league. They have under normal seasons, they have 82 games per season. So N is 82, right? So this is fixed beforehand. So during these 82 games, you may win some, you may lose some. That is a random number. But the number of trials or experiments, the number of times it's run is fixed beforehand. So that's what we mean by a binomial random variable. Okay. The probability mass function of binomial is given here, and it has pretty simple function, p of x, q of n minus x, and so on. Okay. Again, I don't have time to do examples or computational examples. So, so we're getting close to the end of the time, right? So let me. So what I suggest you do is during this week, please go over these notes and find some additional help you need. If you have specific questions, feel free to email me, and try to complete the Moodle quizzes before our next meeting on next Friday, right? And let's see, I will let me try to maximize. Stop share. Okay, so I have stopped the sharing. We have a little bit of time. So if Any questions? We can try, but I'm not going to be doing any new material. If you want to leave, you can leave now. But are there any questions? Oh, okay. So maybe know which section of the textbook you're planning on covering next week. So this is a very good question. What I will do is I will send you a plan for the next lecture on Friday. But I'll do it right a little bit pretty soon, maybe, and a little bit later tonight, right? So you guys can plan ahead, right? I will also maybe, if necessary, I might post some review questions, which we are not grading or anything. You can try them and get ready for the next lecture. Anything else? Okay. I don't see anything other questions. So, so thank you very much for attending the lecture. It's very good to see you, all of you. And I hope the lecture has been useful and you have been able to make sense of it. And so this is a long weekend coming here. Have a good weekend, and feel free to contact me throughout the week. And I will see you guys on next Friday. Bye for now. Bye-bye. Thanks and bye-bye.